Discussion sections up to page 2010, section 24, thermodynamic standard state. Okay, we'll say yes. All right. So, we're going to talk about this again, the standard state. Start from there today. I'll move on. Chapter 20 for you guys, as you're finding, should be mostly review. We're going to look at Hess's law, talk about state functions. We'll also talk about standard state of elements themselves and heats of formation of ions, because as we realize, ions we can't isolate by themselves in solution. So, run through chapter 20 today. Hopefully we'll finish it up and we'll get into new stuff in chapter 21 tomorrow. So, thermodynamic standard state. We use this little degree symbol. Just means a standard state. So you see delta HR 0. That means all your reactants and your products. Underline that. Remember, you're not starting off with just reactants. You're talking about everything in your reaction system. Products and reactants. Pure liquids and solids, already in the standard state. That's easy. Things like reactant water and solvent water. Any solid that you might have, a semi-soluble salt, etc. Things like that. Already in the standard state. You don't have to worry about it. The concentration of aqueous species is always going to be equal to 1 molar. Dr. Horvath also uses a little case italicized M. I just use a cursive M there because I can't draw italics. What does that mean? He's got it right there. 1 big M and 1 little m are about the same. Little m is molality. And that's another measure of concentration. You can measure concentration in a variety of different ways. And what molality is, instead of moles per liter, moles per kilogram of solvent. Now in water, of course, these are going to be just about exactly the same. As we know, 1 cubic centimeter of water, 1 gram, 1 milliliter. Important equivalency. So, we don't really have to worry about how we're measuring our concentrations. You might see it cited with a lowercase m. If it's an aqueous system, you don't have to worry about it, but you might have to do more calculation if you're dealing with a solution of, say, ammonia, something like that. But for our purposes, 1 molar is going to get the job done. So, aqueous species, 1 molar. The partial pressure of every gaseous species is going to be exactly equal to 1 atmosphere. I think more recently, the IUPAC, International Union of Pure and Applied Chemistry, they're the ones that give all the definitions to us. They started using the bar as a standard unit of temperature, but that's okay because the atom and the bar are very, very close to one another. So if you see it cited in bars, you can still use atmospheres because generally our pressures are not too extreme. So these two will be quite close to one another numerically. So another concern there, it's just going to be a small thing, probably outside of our significant figures whenever we're doing calculations anyway. So, remember these two. These are the most important. Pressures of gases, concentrations of aqueous species. 1 atmosphere, 1 molar respectively. Make sure you know that. Make sure that it's products and reactant. If you're ever asked to write something out, write down the reaction, the number of moles or the concentrations of each reactant that refers to the standard state of a certain reaction. You'll know how to write it. Now, a couple additional concerns. Temperature. There is no standard state temperature. You can run a reaction at any temperature, provided all of your system species, products and reactants, are stable at that temperature. You don't want things to fall apart. You don't want things to burn, to ignite. So, no standard state temperature. Most of the time, these things are taken to 25 C, 298 K, but they don't have to be. Pure elements. We'll talk about that in a minute. They have a special definition for their standard state because elements can have different forms of that pure element. So, any questions on the standard state before we move on? This is a very important concept that's going to continuously be applied throughout the rest of the semester. Okay, good. So, next thing we're going to consider. Heat of formation versus standard state heat of formation. Now Dr. Horvath has us considering the formation of liquid water. And he gives us, not even liquid water, just water. Dr. Horvath gives us 5 different reactions there. Each one of them makes water, but since each one of them uses a different number of moles of hydrogen and oxygen, we see that the heats of formation are all different. Now, we need to standardize this. We want a standard state because we want to be able to use one number whenever I'm considering the heat of formation for water. Should I see water somewhere in a different reaction equation, I want to say, okay, I want to be able to apply Hess's law. I want to use the heat of formation of water in the standard state to calculate the heat of a new reaction in the standard state. What am I going to do? Since I have so many options here, I could use O3, ozone. I could use pure monoatomic oxygen gas. I could use O2. I can use a different number of moles of each. Each one of these corresponds to a different HF value. Only one of these is the standard state. Now, Dr. Horvath goes on to explain to us what exactly does a standard state heat of formation apply to. Now, directly from the book, the enthalpy change for the reaction in which 1 mole of the substance in the desired phase is formed. So that's going to kill one of our reactions, reaction number 4, because I make 2 moles of water. I only want to make 1 mole of water. From the required mole quantities of its constituent elements in their standard states at a pressure of 1 bar, pretty much equal to 1 atmosphere. Now, Dr. Horvath says elements in their standard states. What does that mean? Well, I see that I could use ozone, monoatomic oxygen gas, or diatomic oxygen. Now, elemental standard state. Most stable allotropic form of the element. What's an allotrope? An allotrope is just a pure element, and if an element has multiple allotropes, for example, oxygen, O2, and O3, which is also known as ozone, we call these allotropes of oxygen. Now, for the standard state, if I want to take oxygen in standard state, I'm going to take its most stable allotrope. And you can look this up on your table at the end of the chapter, but in this case it's going to be O2. Both oxygen and ozone are pretty reactive species. Oxygen, less so. So O2 is going to be our most stable allotrope of oxygen. You can look this up, and whenever you see an element that is pure, and you see heat of formation of 0 for that element, you have your most stable allotrope. So, it follows from these 2 definitions that are bolded on page 20-11. This reaction, I think it's number 3, corresponds to heat of formation in the standard state for water, because what I do is I take diatomic hydrogen, most standard form of hydrogen, most least reactive form of hydrogen, 1/2 mole of oxygen to make exactly 1 mole of liquid water. All of this corresponds directly to the definition given to us for heat of formation in the standard state. All of these other things are just delta HF, but we want the standard state, something that we can use and continuously apply. This is the one we're going to use. Once again, taking the bare minimum number of moles, the most stable allotropic form of each element, and converting it to the desired phase of 1 mole of my product. All right, any questions on that? Standard state enthalpy. All right. So, question 23. Examine table 1. See if graphite or diamond is the most stable allotrope of carbon. Before you look, make a guess. So, which do you think is the most stable form of carbon? Graphite or diamond? What do you use, pencil lead or diamonds? I hear a lot of people whispering stuff. It's okay.
Seems like it would be diamond, but and then it's graphite.
Feels like diamond, but a lot of people end up saying that. It is graphite. So, we'll find that it is actually graphite. If you go over to your table, end of the chapter, see graphite, heat of formation 0. See diamond, heat of formation 1.895 kilojoules per mole. So, the 2 are close. Now, normally I'd have a set of molecular models here to aid this discussion. However, I can't find Dr. Horvath's stuff. So hopefully I'll be able to have that for you guys tomorrow. More on that tomorrow when we have some molecular models. I'll make a note of that. But graphite is in fact the most stable allotrope of carbon. So that's what I'm going to use if I'm ever trying to make something like carbon dioxide. We'll take a look at that on the next page. I'm going to use carbon graphite. Now I'm not going to say carbon parentheses G because we're not using gaseous carbon. I'm using solid graphite. CGR in parentheses. Okay. So, question 20-4. Appears as if I haven't left space. Write the equation for the reaction for which delta HR corresponds to heat of formation of the standard state for the compound OCS. So we'll note that that's a gas at room temperature, so I'm going to produce that. Let's see here. Go ahead, I'll erase these definitions. All right, so I know this is what I want. OCS is a gas given to us at room temperature. So, I know a couple things. I know I'm going to need 1 mole of carbon graphite, corresponding to the carbon I see there. I know that I'm going to need half a mole of diatomic oxygen. A gas at room temperature. Now, what am I going to do about sulfur? 1/8 of S8. This reaction, as I have it written, will correspond to delta HF standard state of the gaseous OCS molecule. And that's the way that we'll say it. So, do we have any questions here? Basically, all we're doing is we're going through, we can look at our table, which will give us all the information that we need in this case to write down the correct forms of each element. You go ahead, and I realize I'll need to multiply these. Should I have a subscript? Should I have multi-nuclear elemental forms such as O2 or S8? Sulfur forms pretty strong bonds to itself, so at room temperature we have this puckered ring of S8. And then make sure that all the stoichiometry works to give us 1 mole of product. So, those are pretty much the bare bones examples. Everything that we do from now is going to build up on this stuff. So, next page, 2012. Hess's law and state functions. So, before we get to Hess's law, we have to realize, first of all, everything that we've been working with thus far. Delta H, delta S, delta G, all those in the standard state. These are all state functions. Does anyone know what a state function is? It's a shame that they don't introduce that stuff to you in Gen Chem 1 because they did show you Hess's law, right? They taught you about HF and all that stuff. Well, they should tell you about how this stuff is a state function. People get scared of the word function. I don't understand why. All it means is that these functions are pathway independent. So, for example, if I want to make a graph, this is called a reaction coordinate of energy as I go through a chemical reaction from chemical X to chemical Y. Doesn't matter what it is. Now, a lot of chemical reactions are multiple step. I'm going to start here in energy, arbitrarily. Now, I can go to an intermediate that's higher in energy. I can go to another intermediate, lower in energy. and I can bounce back and forth for a while. This is the way a lot of different chemical reactions go. And if I end up with product Y slightly lower in energy than reactant S, I'll see that I have a small difference between the two. Now that's going to correspond to the change in energy between X and Y. So that's going to be delta E. If I wanted to, I can talk about enthalpy, relative enthalpy. And this would be change in enthalpy. Now, regardless of how I get from X to Y, I could use a different catalyst. I could heat it up. I could cool it down. Doesn't matter. This delta H value is always going to be the same. It's always going to be that little bit between, make that look a little bit closer. It's always going to be that small difference between my product and my reactant. Now this can be positive or negative, we know that. Bond improvement, disprovement. But my pathway doesn't matter. Dr. Horvath sort of gives us an interesting parable to illustrate it. He talks about driving from here to Jacksonville, 70-mile trip. Now, if I drive from here to, I think he uses Miami, to Jacksonville, I've driven 1,000 miles or so. But I've still only traveled 70 miles to Jacksonville, if I consider my starting point Gainesville. So, the idea of a state function is that regardless of how I get there, I'm only taking measurements of my reactants and my products. So, it follows from these considerations that if I want to get something like delta HR, delta H0R, delta S, delta G, whatever, all I have to do is sum up that term for all my products and subtract off whatever I need for my reactants. So this is Hess's law. This is presented in many general chemistry textbooks, just as this. Summation of all of my, in this case, heats of formation for my products, less the summation of the heats of formation for my reactants. Once again, pathway doesn't matter. That's all a state function is. But it's important to know the difference between a state function and kinetic function. As you might learn later on, probably in organic chemistry, they'll talk about it a little bit when you're dealing with different reaction mechanisms. But for us now, we're dealing with state functions. All we deal with, products, less reactants. Remember, it's product minus reactants. Remember to distribute your negative signs when you go through here. That's an extremely common problem that we see. You want to make sure to get to the right answer. You take your time. I write out this equation every time when I do it. Delta HF products minus delta HF reactants. If you want to get it right, you want to make sure to keep your negative signs straight. So, that's a state function. Now, application of Hess's law. This is where we're going to go. So, if I take two reactions, like the ones I have written here and here, and I add them together, Hess's law is going to tell me, well, as long as I have products and as long as I have reactants, I can go ahead, add these two together, cross out things that can be canceled, and then all I have to do, apply this formula, and I'll get the change in enthalpy or entropy or whatever I need from Hess's law. It keeps things simple. Once again, the advantage of a state function is not to be underestimated. So, an example. Carbon graphite plus 1/2 mole of oxygen gas gives us CO. This is a reaction. I know it can run because I'm basically burning carbon. So, this is a reaction that I've got. But this is very, very difficult to accomplish in a lab. As a matter of fact, it's nigh impossible, because if I burn carbon in air, this reaction is going to occur. Now you guys know this. If you're at a barbecue and this reaction occurred in favor of this one, the person behind the grill would probably die. Carbon monoxide is pretty poisonous. But, fortunately, carbon and oxygen react 100% with one another to give us carbon dioxide gas. This we know from oxidation reactions. So, how am I going to get at the heat of formation in the standard state for something like this? Because I can't just measure it in a lab. What I can do is I can strategically apply Hess's law and take advantage of a couple of things that I already know. I have those written down here. Yeah. Replace that with a G. Perfect. So, if I take these two reactions, do I have that backwards? That's my problem. I had that one totally backwards. Yeah. If I tried to add the two that I had written up there, I would have gotten a mess. This is a little bit different. So, I can make carbon monoxide in a different way. And I can also burn carbon monoxide. So if I read this reaction right to left, carbon monoxide plus 1/2 mole of oxygen gives me carbon dioxide. Carbon monoxide burns pretty well, as a matter of fact. I can also consider the standard heat of formation for carbon dioxide, which is just what I have written here. Here. Formation of CO2. Now, if I add these up, I'm going to get the reaction that I want. So all I have to do is take my products and reactants. I'll see that CO2 cancels. I don't want any of that. I see it on the product side here, and on the reactant side here. And I also see that I have 1/2 mole of oxygen canceling. So I'm going to have 1/2 mole of oxygen on my reactant side. So to rewrite, now, this is where Hess's law comes into play. I know the 2 delta HRs for this. And I know that delta HR for this corresponds to my heat of formation in the standard state. So you can take those numbers, you'll add them up correctly. Dr. Horvath gives you the sum, so it's no fun. We don't get to do it here. Negative 110.5 kilojoules. And that's for running this reaction one time. So I could say kilojoules per mole, per time I run this reaction to produce 1 mole of carbon monoxide. Now, there's another example on 2013 regarding the reaction of sodium chloride and water to give you 2 moles of sodium metal, 2 moles of HCl, and 1/2 mole of oxygen. Now, Dr. Horvath goes through here. I suggest you give this a read, but since again the answer is presented for you, we won't go through it because you guys can just read about it and how when you dissolve salt in water you actually don't get sodium metal and HCl, because we'd all be in trouble if that were the case. So what we'll do is we'll jump into questions 25 through 28. 20-5 through 20-8. And we'll talk about these. Now, in these cases you are given the answers, but it's not about the destination. So we'll start again with the same reaction that Dr. Horvath gave us before. 2 moles sodium chloride plus 1 mole liquid water. In this reaction, okay, so you'll find from a delta H standpoint, when you go ahead and you read the bottom of 2013 and the top of 2014, this reaction is ridiculous. When you take a look at it from an enthalpic standpoint, because I realize that I go through great bond disprovement throughout this reaction. Now, if I want to consider this through the lens of delta SR, standard state, we'll find something a little bit different. So, what we'll do is we'll go look at our table right at the end of the chapter. And we'll take a look at S values for each of these species in the standard state. It's important to know how to use and manipulate this table. So we're going to get some practice. So, we'll start with product side. Delta HF products, less delta HF reactants. So, for my products, sodium, what's the S value there? 0. S value for sodium should not be 0. 51.2, that sounds a little bit better. 51.2 times 2. 2 moles of sodium. Next, S value for HCl. 186.9. Again, we got 2 of them. S value for gaseous, O2. Make sure you get the right allotrope. I think that's right. Okay. Now, again, we got to be very careful here. I'm going to subtract my reactant. So, S value for liquid water. That's going to be in the oxygen, not hydrogen. Yeah.
How come O2 isn't 0? I thought the elements were always 0.
That's for enthalpy. So you'll find that O2, the heat of formation for O2 is going to be 0 because that's the most stable allotropic state. But for entropy, S, I know that for S, I think it's the second law, thermodynamics. For a perfect crystalline solid, 0 degrees K, S equals 0. So I have a reference point built into the system of the universe for a universal 0 of S, and I measure everything from there. So everything's going to have an S value, and you can actually never have 0 for an S value because we can't get to 0 K. I think we've gotten down to less than a millikelvin at this point. using clever evaporation methods. But we can't get to absolute zero. That's pure theory. For now, anyway. So that's an important point that was probably breezed over yesterday, or not yesterday, on Friday in discussion. But that's a good thing to know, and that's a good question. So for your standard state elements, HR is 0, or HF is 0, excuse me. But the entropy of each element can be measured directly. That's why you see on the table, you see delta HF, delta GF, but then you see S0, because that's just an absolute number. Okay, so moving back to question 25 here. We're going to subtract off our reactants. We want to make sure that we include this negative sign and we distribute it appropriately. So, the S value for water. 69.91 plus twice the entropy for sodium chloride, solid. 72.1. Times 2, yep. Okay. So, what I'll do now is I'll distribute that negative sign. Very first thing, before you start bringing out a calculator or anything like that, make sure you've got it all written down on the paper the way it's supposed to go in, because otherwise you can get things garbled in your head, especially under exam pressure. So, if I want to look for an S value for this thing, 364.66. Now, this unit means this number means nothing because of the reason that I just misspoke. Joules per mole per degree Kelvin is how we express entropy. Because as we know, as we increase temperature, so do we increase entropy. We make things more energetic. We make molecules shake more. We make them bend faster. That's why we include that factor of temperature, especially when you're considering Gibbs free energy. Delta G equals delta H less T delta S. So, joules per mole Kelvin is your unit. Delta SR is what we're talking about. Now, you guys should know this from last semester. I also just said it. Gibbs free energy. We understand a positive Gibbs free energy means the reaction isn't going to go. Not as we have it written anyway, and not at that temperature. Now if I see a positive S value, what does that tell me? Is that favorable or unfavorable change in entropy? A lot of whispering again. I don't care if you're wrong. Unfavorable. Excuse me, favorable. I'm wrong half the time. This is a favorable change in entropy for this reaction that I have written. But we know that this doesn't go. You dissolve salt in water all the time. You don't kill yourself. So, delta SR says go. Delta HR is going to be in charge of this reaction, you'll find. When you take a look at that, you'll find that delta H for this is plus 923.5 kilojoules, which is large and positive, unfavorable, enthalpically. But this reaction will go according to entropy. Remember, you always have to include the 2 if you want to talk about delta G, your criterion for spontaneity. So, any questions here? Basic interpretation of Gibbs free energy? Gibbs free energy, no. Basic interpretation of Hess's law. You guys should know how to do that one. That's a really popular starting point for a question on a quiz or exam. Start with that and then you change it in some way. So that's going to be your first step most of the time. You've got to know how to do that, and you'll always be given all the information that you're needed. Delta HFs, delta HRs, things that you need to do this math. So, moving right along. Question 26. Consider 3 reactions, delta H1, delta H2, delta H3, involving nitrogen, oxygen, and hydrogen. So we're going to apply Hess's law to determine a new HR, delta HR, for a reaction N2 plus O2, giving me 2 moles of NO. So we'll write down that reaction. All right. Now the way I'm going to solve this problem, and the way you should approach it, is realize, okay, I've been given all the information that I need. I just have to read it in the right way. We're just going to take a simple algebraic sum of these 3 reactions given to us, delta H1, delta H2, delta H3, in order to give us 1 mole nitrogen, 1 mole oxygen, to give us 2 moles of NO. All gaseous, very important. Now, first thing that I'm going to do is I'm going to say, all right, I only see one reaction there, and that's delta H2 that involves NO at all. Now, I see I have nitrous oxide as a product here. I have it as a reactant for delta H2, so I'll go through and I'll write this reaction backwards. 5 moles oxygen plus 4 moles ammonia. Reacting to give me 4 moles of my desired product, NO, and the leftovers, 6 equivalents of liquid water. Okay, I'm not done with this reaction quite yet, because I see the reaction that I want to study only has 2 moles nitrous oxide. I've got 4 here, so what I'll do is I'll take my known reaction and I'll divide that by 2. So, what's that going to give me in terms of H2 for delta HR? How does he label them here? Delta H2. So it's not just delta H2. I've done 2 things. I've divided it by 2 and I've reversed it. So how is that going to look like if I'm trying to operate on H2? So I've divided it by 2. I got to make it negative because I reversed the reaction. So the sign for enthalpy is going to be reversed. So there's my first step. I see that I need delta H2 over 2, negative. Next thing that I'm going to do. Okay, well, I'm definitely not there yet. I see ammonia here. I see water here. I see extra oxygen here. I'll be able to operate this a little bit later so I can cancel those extra 3/2 of an oxygen. So, next thing that we'll cancel, you can do it either way. Let's take advantage and get rid of ammonia. So the reaction that gives us ammonia, because I have ammonia right here, is going to be nitrogen plus 3 equivalents hydrogen to give you 2 equivalents ammonia. Once again, all gaseous. When I'm looking up numbers here, we're not going to do it for this problem. I want to keep close track of that because oftentimes we do have data for these things: gaseous, aqueous, solid, liquid. In this case, we're dealing with ammonia gas, yes. So, what I see here, I think I've done a good job. this is probably all I need because I see I've got my 2 moles of nitrogen gas covered. I can also cancel my 2 moles of ammonia. So I'll take this one as is. If I want to talk about it in terms of delta H1, identity, just delta H1. All right. Now, what else do I need? I need to cancel 3 moles of water. I'll use my last reaction. Delta H3, liquid water, going to H2 gas plus 1/2 O2 gas. All right. Now I see here, I'm going to have to cancel 3/2 of O2 gas. I've only got 1/2 here. I also need to cancel 3 moles of liquid water. So I'll simply multiply this reaction by 3. And the FET's giving me 3 times delta H3 is this one. So I can go through, double check myself. 3H2, 3H2, those cancel. 3/2 O2, 3/2 O2, also cancel. Similarly, my 2 moles of ammonia and 3 moles of water. So, have we done it right? I crossed out all 5/2 of oxygen. So, yes we have, but I'm left here . 1 mole of O2. So, N2 plus O2, giving me 2 moles nitrous oxide, NO. Now, Dr. Horvath asks us to apply Hess's law to determine HR in terms of delta H1, delta H2, delta H3. We can handle that now. I know from Hess's law, all I have to do is add these up correctly. You can do this for any number of reactions, provided everything cancels and I have no stray terms left over. Well, I'm looking at my last one. Yes?
What's the first thing you look at when you do a problem like this?
When I do a problem like this, I look to find one product.
Okay.
And then from there you can go ahead, you'll see what other things you have left over. For a problem like this, you'll always have all the tools you need to solve it. So you can really start any way you want to. You could start with 1 mole of oxygen here and then go. If I started, however, with this mole of oxygen gas on my reactant side, I'd realize I'd get into a little bit of trouble later on because this reaction would be reversed and I would never be able to have nitrous oxide as a product. So you can sort of double check yourself as you go through. As long as your problem solving methods are sound, you'll always get to the right answer. So any other questions on 20-6 before we go ahead and move on? Okay, so question 20-7 is for you guys. I would suggest you go ahead and do it. Make sure you get the practice. Once again, it's always easy once you know how it's done, once you know the answer. He gives you the answer. I double checked it myself. I got 818.3, close enough. Maybe I missed a decimal in there somewhere. So, we'll jump on question 28. We're comparing water and H2O2. Hydrogen peroxide. You know, you use hydrogen peroxide, you get a small cut, you pour it on there, it hurts like hell. No more germs. You live to see another day. Now, Dr. Horvath gives us a hint as how to do this. We want to compare the thermodynamic stability of each. Which one is more thermodynamically stable? Hint. Compare their Gibbs free energy of formation values in the standard state. This is something we can pull off of our table. We could do it ourselves, but we have the information available to us. Now, for water, I got negative 237.1 kilojoules per mole. For H2O2, I got negative 120.4 kilojoules per mole. So, which one of these is going to be more stable based upon Gibbs free energy of formation, standard state? We'll take a step back from there. What does a negative Gibbs free energy value mean? Negative delta G.
Reaction will go.
Reaction will go. So what does a more negative delta G mean?
More reactions will go.
More reaction will go. That tells me that this product water is more stable than this product H2O2. If you can't see my decimal points, it's going to make these numbers look really weird. So, by about 117 kilojoules per mole of reaction, water is more stable. And we'll find this from structure as well. H2O2 contains what's called a peroxide bond. That's why we call it hydrogen peroxide. Peroxide bonds are notoriously weak. In aqueous solutions, such as your blood, they readily undergo heterolytic bond breaking because, once again, the electronegativity of oxygen is equal to the electronegativity of oxygen. That weak bond falls apart, and you're left with two hydroxide radicals, which attack anything that they can to form an oxygen heteroatom, something different bond. Radicals are not stable. So, that's why hydrogen peroxide is such a potent disinfector, because it basically kills the first thing that it sees in order to relieve that weak OO bond in that radical formation. H2O2 is less stable by a small landslide. You can also go and compare delta HF and delta SF values. You can add those two up and you get something very close to the Gibbs free energy of formation. If you're interested, I would do so. All right, so any questions on this stuff? Relative stability as viewed through the lens of Gibbs free energy of formation? Okay, pretty simple. Next section, 25, heat capacity, specific heat capacity, calorimetry. Calorimetry. Heat capacity, Horvath's definition, quantity of heat which the substance must absorb to increase temperature by 1 degree C or 1 K. The two are equal. Now, this property depends on the amount of substance. So, there are two different heat capacities that you'll see. You'll see molar heat capacity. You'll also see specific heat capacity. We generally deal with specific heat capacity because it's very easy to determine the mass of something. So, specific heat capacity. If we want to come up with a definition for this term, I would say the amount of energy we generally express it in joules needed to raise 1 gram of your sample 1 degree C. So it's going to follow. You'll look at the units for specific heat capacity. Joules per gram per, call it Kelvin, degree C. Same thing. Once again, that makes it easy. So this is an important unit to know. You want molar heat capacity? You guys know how to go from grams to moles, not a problem. So, this semester in this class we'll deal with specific heat capacity a lot, but again, going from grams to moles, easy as knowing your moles, so you guys will be able to do that should you ever be faced with such a question. Now, heat capacity is very important. We're given a list of heat capacities here, page 2015. Solid water, liquid water, gaseous water, sand, aluminum, iron. See the highest one by a lot. Liquid water, more than double that of solid water. Now, you guys have probably been taught this, high school, maybe last semester. Water has a pretty high specific heat capacity, 4.18. Joules per gram per degree Kelvin. Compare that to, I don't know, a pure sample of some metal, iron, 0.45 joules per gram per degree Kelvin. Now, this is of utmost importance to us. Our Earth is covered, I don't know, 75%, 2/3 water, something like that. Water is the great heat sink on our planet. Otherwise, when the sun came out, it would be super duper hot, and when the sun went down, it would be super duper cold, and we would not be alive. That's all due to heat capacity. There's a bunch of water around us, keeping this room at an ambient temperature. Otherwise, those of you sitting in a sunbeam, if any sun fell on this room, would be unbearably hot. And those of you sitting in the shade would be quite cool. So, heat capacity of water, important point to know. Now, a couple general questions about heat capacity. Give 3 properties of aluminum and iron, for which we just looked at the heat capacities on 2015, 0.89 and 0.45 joules per gram per degree Kelvin, respectively, which serve to explain why these metals are excellent materials from which to fabricate cookware. So, I'll give you the first one. Low heat capacity. It's very easy to heat up a pan in comparison to heating up a pot of water, right? So, they heat up easily. They're good at heat transfer. What's that? All right. So, any other thoughts of properties of aluminum and iron which make them good things for cookware? You ever melt a cast iron pot in your kitchen? No, you haven't. High melting point was a good one. Did you just say that?
No.
Oh, okay.
I was thinking for you.
All right. The last thing. Any other thoughts on why aluminum and iron make good cookware? Well, I heard the word malleable thrown around. Now, specifically, solid iron and solid aluminum are not very malleable by human hands or in kitchen conditions. So I would say not malleable. Yeah, frying pans probably hurt. So, those 3 reasons, just sort of general things. That's not really a chemistry question beyond low CP, high melting point, things you guys already know. So, question 2010, let's do some math. Yeah. What is the mass of liquid water that warms 25 degrees Celsius, or 25 K, on absorbing 55 joules of heat? So, I can use this to tell me the answer. So I know that my heat capacity for water, 4.18 joules per gram Kelvin. I'll set up an equivalency using the information given to me. 55 joules. I'm looking for grams. We call it X. X grams times what? 25 degrees times 25. I won't say degrees C because I said Kelvin right there. So, all I have to do is go through, solve for x. Generally when I do this kind of thing, I remember my units. Sometimes I'll drop them while I'm doing the math. Makes it a little bit easier for me to look at without getting a headache. But make sure you know the unit that you're looking for. And you will get this answer after going through solving this simple proportionality. I got 0.53 as well. All right. So, how do we get at heat capacity, specific heat capacity, things like that? Calorimetry. I would go ahead. Generally in this class we don't talk very much about it. Read that section. See if you can answer question 20-11. That's good material to know. Make sure that you understand where internal energy comes from. Yeah?
On the last problem, could you change it to Kelvin?
Yes.
Oh, no you don't. Because we're dealing with the change in temperature.
Okay.
Yeah, so the change is 25 degrees C, so it could be 0 to 25, it could be 1,075 to 1,100. What's that?
How do you know you're dealing with the change in the waters?
Because this K right here, so I've got the amount of energy required to raise 1 gram, 1 degree. So I know I'm on a per degree basis. So basically, warms 25 degrees. 25 degrees is going to be my change, which is the Kelvin here. So if I'm using a not constant term, I could put a delta K in there, if you're really interested in that. But generally, people just express that as a Kelvin or a degree C. That's a good question. Got to be the change. So let's see here. Calorimetry. Back to question 2011. Make sure you understand where internal energy comes from. If you don't, just have a read on those first couple of pages. Most of that stuff should be sort of review for you guys. Make sure you have a good general understanding of where these things come from, how they're derived. Of course, you don't have to memorize all the mathematical equations. You guys aren't physical chemists, but you should have a good idea of from where this stuff comes and how it all sort of makes sense. So, let's see here. What's a hard one? 20-12, that's a very similar question to 2010. Take a look at that. That'll be practice. Okay, here's a good one. 2013 is a little bit different. Now, what I'm doing is I'm taking 200 grams of solid iron at 100 degrees C. I've got it in the oven. And I immerse it in 500 grams of water, 500 mils of water, at 25 degrees C. I'm going to calculate the final temperature of the entire system because I know this thing's going to come to equilibrium. Eventually, my iron plate and my water are going to be the same temperature. Now, how am I going to do that? So, for starters, I'll take the two numbers that I know. The heat capacity for solid iron is 0.45 joules per gram per degree Kelvin change. Say that. And for water, .18. Again, much larger. Same unit. Joules per grams per change in temperature. Now, how am I going to go about this? Well, first of all, I've been given some information, and I'm going to take advantage of that. So I'll go ahead. I'm going to start reorganizing iron and water. Now, That's an easy one. I've got 200 grams of iron in this experiment that I'm running. I don't know what my change in temperature is. That's what I'm trying to get at. So, if you want to, call it X Kelvin. Now, I also don't know the amount of energy that's been transferred from the iron to the water. So I'm going to call this Y. So this is just the heat capacity for iron. I know that if I transfer a certain number of joules from a certain mass, and I have a certain change in temperature, this proportion is always going to be 0.45. The units are the same. We'll write them down. Now, one equation, two variables. No, no. I'm going to do a similar thing for water. Once again, I've got 500 grams of water, right? Okay. Now, I'm going to have to think about this. We'll do the easy one first. How many joules am I going to use? What variable should I use for that? I think I heard somebody whisper it again. I'm going to call that Y again, because I know, since I have a closed system that's not going to lose any energy, the number of joules that I transfer from iron is going to be equal to the number of joules absorbed by the lower temperature water. So I'll call that Y joules again. Now, I want two equations and two variables. What am I going to use for my change in temperature for water? Okay. Now, if I go through and I solve that, I realize that that might be true if their heat capacities were the same. But since I've got more water and the heat capacity for water is appreciably larger than that of iron, I'm going to have to do something a little bit different than just call it X, because I know that the iron is going to cool down more than the water is warmed, because it's tougher to heat water up. Question?
I was going to make a guess.
What you got?
Could you do 4.18 divided by 0.45x? You just took the ratio of your heat.
Okay, you might be able to do that, but I can do it a little bit more simply than that. Now, I realize I've got two temperature limits here. 100 degrees C is where the iron's at. 25 degrees C is where the water's at. What's my maximum change in temperature if the heat capacity for one of these approaches 0? 75 degrees. So I'm going to call that 75 minus X. Because I know the most that my water can increase is 75 degrees. But it's not going to increase all 75 degrees. I've still got a number for the heat capacity for iron. So its change in temperature is going to be my maximum change in temperature less the change in temperature that I have on the left-hand side for iron. Now, are there any questions on how I chose that?
Why does Q equals MCAT not work?
What's that?
Why does Q equals MCAT not work?
Yeah, I just did it
I
as
could do
like
that.
MC delta T equals negative MC delta T, and it came up with the same answer.
We can do that too. I suppose I took the long way. All right. Well, either way you do it, as long as you come to the right answer, I guess that's good. Okay. So, anyway, stealing my thunder, guys, again. 28.1 degrees C. So you'll notice that the water heats up 3.1 degrees, and the iron cools down much, much more. All right. So similar question, 2014. You guys can go ahead and do that. More practice. 2015, ice weight reduction diet. Now, what we'll do is we'll start with this one tomorrow. I'm going to say, give this a try for tomorrow. Beyond 2012 and 2014, that'll be practice. Come in with an answer for 2015, yes or no. Is this a reasonable way to combat weight gain? We'll start there tomorrow.